In the previous video, I explained with one example how to compute the volume of certain solids by slicing them like a carrot. That method is sometimes called the washer method. In this video, I will work with a different example that will require a different approach, sometimes called the cylindrical-shell method. Do not worry about the names. Both methods are about slicing the solid, we just slice it in a different way. Here's the example. I will look at the region in the first quadrant between the graph of y equals 2x to the 4th minus x to the 5 and the x-axis. I will rotate that region around the y-axis. This creates a slowed of revolution and I want to compute its volume. I invite you to pause the video, draw a picture, and try to visualize what this solid looks like. Once you think you understand what it looks like, once you have a clear picture, continue watching. This is what the graph of y equals 2x to the 4th minus x to the 5 looks like. I want to take the region between the graph and the x-axis, and I'll rotate it around the y-axis. What do I get? I get something that looks like this, like a little volcano, a mountain with a hole in the center. Why? Look at the rubber band. The rubber band represents this curve, and the y-axis sticks out from the center. Then take the region under the curve, that's the region under the rubber band, and now rotate the rubber band. That's why the solid looks like this. Now, I want to compute its volume. First, I'm going to attempt to do the same thing I did in the previous video. I will slice it like a carrot. Here's my knife, I want to slice it like this. If I do that, what will each piece look like? Something like this. That's a cut. Here's another way to look at it. I can cut a very thin stripe with width dy. If instead of rotating the full region, I just rotate this stripe around the y-axis, it will produce something like this. Notice that it is not at scale. The thickness of this ring is dy. Let me give names to the other dimensions. I have the inner radius, call it little r, and then I have the big radius, call it big R. If I look back at the region here, I see that this is the big radius and this is the small radius. Next, I want to figure out what the volume of this piece is. It's going to be an infinitesimal volume because this annulus has an infinitesimal height. That's the infinitesimal dimension. What will the volume be? It's going to be the surface times the height. The height is dy. What is the surface? It is like a big disk that is missing a smaller disk. So it will be the surface of the big disk minus the surface of the small disk. Excellent! That is the volume of one infinitesimally small piece. To get the volume of the full volcano, I need to add up all the infinitesimally small volumes. That sum is actually an integral. So the volume will be the integral of these pieces. I am just copying the same expression. What are the endpoints? Well, I'm integrating with respect to y, so it will go from 0 to whatever the maximum value of the function here is. I don't know what that is. I'll call it b. I'll figure out what b is later. To finish the setup, since I'm integrating with respect to y, I need to write everything in terms of y. Well, big R and little r are values of x here. So I need to solve for x. In the equation y equals 2x to the 4th minus x to the 5, I expect I'm going to have two solutions in this domain. The smallest one will be little r, and the bigger one will be big R. That's it. I finished the setup. I have a plan. Unfortunately, I don't think this is going to work, because I don't know how to solve for x here. If the function had been different, this plan would be great. It would work beautifully. But as it is, I cannot fully implement it. So this was a good idea. It was worth trying it, but ultimately we cannot complete the problem this way. I'm going to have to try something else. Here is the original region again. In the first method, I integrated with respect to y. I slice the original region horizontally. This time, I want to integrate with respect to x. I'm going to slice the region vertically. Specifically, let me look at a very thin stripe with thickness dx. I want to see what I get when I rotate this thin stripe around the y-axis, and my full solid of revolution will be the union of those pieces. I get something that looks like this. Here's another way to look at it. This is the volcano. In the first method, I was taking cuts like this. But this time, I am taking concentrical cuts, and this is one of them. This is sometimes called a cylindrical shell. And there is a big difference between the two cuts. In the first method, the infinitesimally small dimension is this height. But in this second method now, the infinitesimally small dimension is this thickness. Let's find out the other dimensions of this piece. The height is y, and the radius is, well, the distance to the axis, which in this case is x. Notice I will be integrating with respect to x. I will want to write everything in terms of x. Now, how do I write the volume of this piece? Precisely because the thickness is infinitesimally small, I can just break it and stretch it like this. And now this looks like a brick, and it's easy to compute the volume of a brick. Notice that, strictly speaking, this is an approximation and we make a tiny error. But it's an okay approximation precisely because the thickness is infinitesimally small. If I try this with something else where this dimension were normal, then I would be making a big error. Okay, as I say, the thickness of this is still dx. The height is still y. What about this dimension? Well, it's the length of this circumference, and the radius is x, so that length is 2 pi x. Now I can write the volume of the brick. It's the product of the three dimensions. It's an infinitesimal volume, because one of the dimensions is infinitesimal, and as I said, it's the product of all of them, 2 pi x times y times dx. Excellent. That's the volume of one piece, and my solid is the union of all the pieces, so I have to sum them, or rather take an integral. Since I am using x as the variable of integration, it's easier. It will go from 0 to 2. And now I copy the infinitesimal volume. It's 2 pi x times y, but I need to write everything in terms of x. So I put 2x to the 4th minus x to the 5 times dx. Success! I've managed to set my volume as an integral. Everything is written in terms of x only, and x is the variable of integration. We can complete the calculation from here. These two methods to compute the volume of a solid of revolution have official names. The first one, when we cut the initial region perpendicular to the axis of revolution, is sometimes called the washer method. And the second one, when we cut the initial region parallel to the axis of revolution, is sometimes called the cylindrical-shell method. But I don't care about the names. I even think that the methods are basically the same. Cut the solid into infinitesimally small pieces, that's it. We just happen to cut in different ways. Nevertheless, whatever you call them, if you want to practice the second method specifically, here is an exercise. The volume of this solid of revolution is particularly well suited for the second method, but not for the first one.